Buschek. So also on behalf of my co-author Florian, I'll talk about our work on ProbUI, which is a framework for creating mobile touch interfaces. And in this work, we explore ideas on how we might integrate more advanced ways of specifying UI elements or specifying how to activate UI elements. And let's start with a look at the current way of representing targets in mobile touch interfaces. And that is your typical bounding box. So usually we use boxes to describe the target areas in mobile touch interfaces. And that is the case in Android and iOS and on the web. And there's a one-to-one mapping. Typically, there's one box for each element, so your typical button is just a rectangular area. And the decision, so if there is a touch event, then the decision is a static test, so deciding which button the user has pressed is based on checking if a touch point falls within a certain rectangle. There are some problems with this approach, so here are two situations where there might be a problem. So on the left-hand side, maybe the touch point is just outside of the bounding box, but probably the user still wanted to activate that button. And then on the right-hand side, it's not quite clear which button the user wanted to press. Maybe the one where the touch event was registered is not the right one from the user's point of view. Then another problem is that beyond the simple tap, there are other little gestures that have been proposed in the literature, like sliding or crossing a widget to activate it or encircling it. Some of these might be more suitable for people with motor impairments, for example. And it seems a bit odd that we have this static box model for something that consists of more than one touch event that has a temporal dimension, basically. Okay, so what's the contribution of this work? So we start with this view that boxes might be just one way of describing the expected behavior for a target that the user then needs to match, basically, to select that target. And then with that in mind, we can think about some ways of generalizing that. And this framework, we explore 3 generalizations and kind of summarize that as going from bounding boxes to bounding behaviors to convey this more general view. So the first generalization is that we want to account for these dynamic behaviors that we've seen on the previous slide. We also want to break this one-to-one mapping, so the framework will allow us to specify more than one way of activating the same interface element, and we will see some benefits of that later. And then finally, instead of having this discrete, simple geometric test, we want a probabilistic model, and we will also see benefits of that. And then some of these ideas have been explored in other work as well. In this framework here, the particular idea is that we can derive the required models automatically from the existing bounding boxes and some additional declarations. And the idea behind that is that this is then easier for developers to integrate. Quick look at related work. We will talk about 3 related areas or 3 related frameworks. There's first the idea of specifying gestures with symbols. This is a figure from a paper by Kin and colleagues from 2012 from their framework called Proton, and they introduced the idea of using regular expressions to describe gestures. And you can see tokens like D for a down event, M for a move event, and U for an up event, and then some modifiers. There are other tools or other approaches to modeling gestures, in particular in a probabilistic way. Here's a screenshot from Gesture Studio, which reminds us of a video editing software. So you can create these gestures by demonstration and then edit them and combine them and cut them, and then eventually you can export the recognizer and integrate that into your program. And then finally, there are frameworks like this one from Julia Schwarz and colleagues from 2011 that take a probabilistic input event, for example, from such a recognizer, and try to process that in a way for some benefit for the user, maybe adapting the interface, or if it's not clear what the user wanted to do, then maybe there's an additional confirmation dialog coming up or something like that. And if we look at these on a more abstract level, then we can find some advantages and disadvantages. So for example, if we can express gestures with symbols, once we've learned to do that, then that might be easy and readable. It doesn't require training data, but it usually does not give us probabilities. Then on the other hand, if we have a probabilistic approach, we do get that, and we can also model more complex gestures, but this might be harder to learn or use or integrate into your application, and it requires collecting training data. And then finally, if we have a framework for probabilistic interfaces, then we can handle uncertainty, for example, based on the input probabilities, but we require some way of getting those in the first place. Now, what we explore in this framework is to take some ideas from these three related areas and try to combine them and put them into some kind of pipeline. And let's talk about that. So here's an overview. We start on a very abstract level and then make it more concrete with examples. So looking at the developer's role, as a developer of a mobile app, for example, I would describe some or define some behaviors that I expect in my application. This could be a tab, a slide, other stuff, and this, for this we use a language similar to that of Proton. I can also define rules, like for example, I want to check if the user completed a slide, and then I want to do something so I can add some callbacks to that. And we have this interpreter that takes these elements and derives a simple probabilistic model in the background, and then on the user side, this model provides live updates during interaction and on the selected target and other things. And this could be used, for example, to just highlight the most likely target. Okay, let's first start with how we set up these behaviors. And this is fairly close to Proton. So we have some tokens like north, south, west, and east that describe areas relative to a UI element. And that's the main difference to Proton here. So everything is always relative to a particular UI element. There are other tokens you can use to describe, for example, touching the center of the element and so on, and you can combine those to more complex expressions. The other thing we need to describe gestures is basically to just chain these areas, and we do that with these little arrows, and you can see that there are two kinds of transitions. There's a one-way transition, a two-way transition. So for example, sliding left to right, that's just L arrow R. Or if in the rubbing example to the very right, if we don't care about the direction, we can use this two-way transition. Okay, so I'm skipping the rules and callbacks here for the sake of time, but they are described in the paper, of course. So let's take a look now at how we derive these probabilistic models from these behaviors and the other components. And the basic idea is that we try to map these boxes from find a mapping from the bounding boxes to sequence models, and we use a simple hidden Markov model. Here's some intuition. If we start with a box, we can replace that with a distribution, a Gaussian, as commonly done in adaptive keyboards, for example, and that allows us to take a first step towards a probabilistic world. If you think about how we would integrate a simple gesture with boxes, then we might have a slide like, okay, there's a touch event in one box and another touch event in another box. And again, we can fairly directly translate that into a simple graphical model. So that's what we do. Here's a visualization of some examples. So the circles show the sigma ellipses of the distributions, and the arrows show non-zero transition probabilities. In a bit more detail, to set up an HMM, we need to define the location of these states, so the means, and we can derive those from the given bounding box, the location of that interface widget, and the area tokens. We also need to define the size, so to say, so the covariance structure, and that is done by using the size of the widget with some prior scaling factor, and you could have different ideas of what would be suitable here. And then finally, for the transition matrix, we can derive that from the transition tokens. We also need to describe the likelihood of starting it at each state, and that's basically the left-hand area, or if there are two-way transitions, then it might also be the last one. So basically the order of the tokens gives us that. Okay, so how can we use that, or how would we use that to develop something? So here's an example widget, a play button, which has your typical play pause functionality. So if you tap on the button, it switches between play and pause. And to make it a bit more interesting and highlight this idea of having multiple behaviors, we add some additional gestures to it. So if you slide to the left and right, you trigger fast forwards and backwards. If you keep on sliding further and release the finger, then you skip forwards or skip to the previous track. We can set this up by describing these behaviors with the tokens as introduced on the previous slides. Then we would also set up some rules that might say something like, okay, the slide to the right has just been completed and is the most likely behavior that the user performed, and then that might trigger fast forward, for example. Okay, and then in the background, the system derives these simple models. Now, moving on to inference. So during use, let's say we have this button that we just created. We also have the, if this is a music play application, for example, we might have a slider representing the timeline. So there are at least two elements in this example. And now the user starts sliding on the button. And what the system then does automatically in the background, it infers the likelihood of the user's behavior for each of these elements. So let's say our button has these 5 possible ways of activating it, as described on the previous slide, and let's say the slider can just be used by sliding to the left or the right, and you get some probabilities of how likely it is that the user wanted to do that kind of behavior for that element. And then integrating over those, we also get another set of probabilities which describes how likely it is that the user actually wanted to use that element. And so the intuition here that's realized by the system is that the most likely target is the one for which the expected behavior, or the currently observed behavior best matches with the expected behaviors. Okay, so as an intermediate summary, we try to move from the world of boxes to a more general view, and in this case we introduce sequence models instead of simple boxes. We also allow the developer to specify more than one behavior per widget, basically rendering each UI element a little gesture classifier. And since this is to some extent probabilistic, it can account to variations of the way the user executes these behaviors. Now, what can we do with this? So here's a set of examples. So one way of making use of the fact that you can expect more than one behavior for each widget is to build an adaptive interface. And in this set of examples, we adapt to left-handed or right-handed use. So here you can see me trying to reach a slider that's too far away, but the slider recognizes my movement arc and then adapts and bends to match my trajectory and move into reach. And it would do it from the other side if I were to use it with the right hand. In a similar spirit, we have this menu here inspired by Google's material design floating action menu. Can use it in a normal way. However, if I would try to use it with my thumb, I might not be able to reach the upper elements. If I do this little flick, then it moves around the elements in a bended way. And the idea is here that here we implemented first the normal tap that opens the menu in a straight fashion, and also this alternative way of activating it with this flicking behavior. And the final thing, so here's a contact list with buttons on one side and the names on the other side, and it switches the alignment so that the buttons are always close to your thumb, and the thumb does not occlude the text. That's the idea. Okay, so that brings me to my summary and conclusion. So we started with this idea of moving away from boxes to something more general, and this has this bottom line, or this underlying view that boxes or something else describes the expected behavior for an interface target that the user then needs to match. This has several advantages. So if we use sequence models, we can better account for little touch gestures instead of just a tap. We've seen some examples here. There are a few more widgets in the paper. Then we've just seen that if we can specify multiple behaviors per target, that facilitates building adaptive UIs, and we've implemented some examples adapting to left and right-handed use. And then finally, since we have probabilities of activation or using a specific kind of gesture for a specific element, we can use that to give some feedback. So for example, on the right-hand side, you can see that if I touch in between the two sliders, it gives me this transparent preview. And to implement that, it is useful to have these probabilities. And it could also be used for mediation, so inferring what the user wanted to do. There are some limitations. So the probabilistic model is fairly simple because we want to be able to derive it automatically from the boxes and the declarations. So it's not learned on data. Also, the probabilistic nature really just captures the touch trajectories, but not, for example, the states of the UI. You could build that on top of it using the probabilities provided by our framework, but you would have to do that yourself. And then, of course, specifying gestures by declaration might be convenient, but it clearly has limitations. So if you think about these short gestures for activating interface elements, that might be fine. But if you think about more complex shortcuts, maybe not related to UI elements, then you might be better off with collecting training data. For future work, we could, of course, try to extend the declarative language, which with additional operators and so on. I think what's more interesting is to think about how we could learn or refine models from data. So take all of that and use it as a prior to specify the interface and its behavior in the beginning. And then similar to adaptive keyboard, as the user keeps on using the interface, you could retrain and refine the models from data. And then finally, the generalization does not have to stop at touch. So we could think about adding behaviors that describe shaking the device. Maybe in our play button example, that would be a shuffle functionality. And then the challenge is how do we infer the user's intention across different modalities. Okay, that's it. I thank you for your attention, and I welcome your questions.
Hey, I'm Dominic from the University of Washington. I really like this work. It really makes you think about, I guess, a different part of the design space and new interaction methods, and also kind of describe them in a new way. One thing I'm a little bit worried about is that one of the main properties of UI interfaces is one of the important properties is that they are predictable, that its internal state is obvious, and that interactions are discoverable. Don't you think that making things probabilistic makes it much harder for people to understand what it actually means to click on a button? And don't you think that this kind of violates that principle?
Yeah, so I mean, a good point, thanks. So of course, it should not come across as every element has to have these huge set of different ways of being used, but for some elements it might make sense. And then the question is, how do you give the appropriate feedback, feed forward? And there are techniques. So for the slider example, it would preview the bended version, for example, before doing that. And to implement such feed-forward mechanisms, it is useful to have the probability. So I think it depends on what you do with the probability. So the framework is at that point, it's not on that level, but it would provide you as a developer with these probabilities, and then you could look into literature, for example, into implementing different feed-forward mechanisms. But of course, there is a danger of adding too much or making it not clear enough what could happen, what is there. It's not as discoverable as just having the simple model of if I press there, then that clearly activates that, yeah.
We have time for one more question.
Orestes from Ultra Haptics. Going beyond the touchscreens, maybe in gestures in 3 dimensions?
Yeah, would be possible as well. So it's partly implemented in a way that you could add other sensors fairly directly. So you could think about the accelerometer or maybe even some external tracking if you want that. Then you would have to pipe that into the device, of course. So this is all running on the device at the moment. But conceptually, yeah, there's no reason why it would be limited to just touch. Yeah.
Okay, let's thank our speaker.
Thank you.